partitioning for trajectory tracking. Okay, so q as a function of time is given. We want the, draw this in red. So this is the goal is track this trajectory. Okay, so let's call that QD. That's the desired and a good a system which is well designed will track that trajectory exactly, right? That's what you wanted to do. So how do we go tracking? So far we've only looked at set point tracking. So we are not given the trajectory, but we're given the initial point, final point. We don't care about how the robot follows that trajectory, but here we are concerned about how the robot follows the trajectory. So QD of t is given. If QD of t is given, Q dot t is also known. Well, Q dot t, also Q double dot t is known. Okay, and where does it come from? Well, we've already talked of trajectory generation, where initial position was given, final position was given. We also specified initial velocity, initial acceleration to be 0, final velocity, final acceleration to be 0. Based on that, we created a time profile, which was a polynomial, and that gave us QD of t. And by differentiating, we get a velocity and acceleration. So we already have that information. We now have to track it. So what we'll do is we'll use this control law. And this is just a modification of the control partitioning control law we talked about earlier. M, which is an estimate of the mass matrix, Q double dot minus KP Q minus QD minus KD Q dot minus Q dot D plus C hat, which is an estimate for Coriolis term, plus G hat Q. Okay, so this controller I'm going to claim is going to achieve our goal of set point tracking, or sorry, trajectory tracking. Okay, so why is this true? So this is analysis to show that tau is able to track. And we'll do it only for this special case. We have a perfect estimate of the mass matrix, the Coriolis terms, and the gravitational terms. Okay, we have perfect estimate. So now what we'll do is we'll put this, the equation of Manipulator is the mass times Q double dot plus C times Q dot plus G of Q equals tau. So let's sub in sub 1 in this equation, M Q double dot plus CQ dot plus GQ. Of course, I'm going to live with the I'm going to do the special case where I know the mass perfectly and the C and G perfectly. So this is going to be, tau is going to be mass times Q double dot D minus KP Q minus QD minus KD Q dot minus QD dot plus CQ dot plus GQ. And so what we can do is we can cancel off the terms which are common, and we are left with M Q double dot minus Q D double dot plus KP. So let's maybe put KD first. Q dot minus Q D dot plus KP q minus qd equals 0. And I can write this as mass times E double dot plus kd E dot plus kpe equals 0, where E is q minus qd. That's the error between q and q. Q is what the manipulator actually does. Qd is what we want the manipulator to do. And ideally q equals qd if it's perfect. You look at this equation, that's the equation of a spring mass damper, right? If you design Kp and Kd right correctly, then you should get, you can do whatever you want. You can do under damp, over damp, or critically damp. In this particular case, we only look at, we'll try to do critical damping because that has no overshoot, it has fastest control. So this is.
Sorry, you said Q is the trajectory, the
Q is what
it does, and QD is what we want.
Yes, right. I'll write it here. Q is actual motion, QD is desired motion. So I'll write that again. It's ME double dot plus KDE dot plus KPE equals 0. This looks like a spring mass damper system. So we, okay, by choosing Kp, Kd, we can get the system to be critically damped. Okay, so what you do is simply put Kd equals, am I doing a mistake? Hold on. Yeah, this is not right. I'm just missing a small thing here. This should be this way, right? Because there's MQ double dot and there's M here, so I have to pull it out. So this should be what, this is what it is. The M comes out, it sticks out. Sorry about that. Right? There's M here with M here. When I get it in here, the M comes out common, but M is also multiplied with all these things, so it has to come out. This time. So M it should be outside the bracket. This is what it is. So I made a mistake, so I'm going to fix that in my second page. This particular thing looks like a spring mass damper system. In particular, this is a spring mass damper system with a mass equal to 1. Or in this case, it's actually not 1 because it's a matrix, so it's identity. So what we do is, to make the system follow the trajectory and be critically damped, we say Kd equals 2 square root Kp. That's all. So this is the standard control partitioning control law. If you choose this, you get critical damped system. Okay. So as I said, it's always useful to have a block diagram. That's how people communicate controllers for systems, and this is not going to be very different from the block diagram we've seen for control partitioning. Okay, it's sometimes really hard to imagine, to figure out the exact space one needs to draw these figures. So let's put the system first. MQ double dot plus CQ dot plus GQ. That's our system. Let's stick an arrow there. What comes out of the system is Q dot and Q. Those are the two measurements, position and velocity. Let's take that measurement and feed it. Take Q, multiply it with our estimate G, and feed it back. So this is going to be tau clearly. So let's feed it to this block. We take Q dot, multiply it with our estimate for the Coriolis term C hat, and then feed this back to the loop. Okay, and this is a positive feedback. And then, so there's no feedback, that's feed forward. And then let's now, so this is taking care of, so remember our control law was tau equals m times q double dot d minus kp q minus qd kd q dot minus qd dot minus cq plus cq plus gq. So the c hat and m hat. So this has taken care of these terms. Now I need to find these terms, which is basically taking q, subtracting it from qd, and thus qd and qd dot are references, they have to come externally. So what I'm going to do is take this q dot, okay, and q t dot is something which we supply to it. It comes from a table or whatever you like. And then we have to take in this is q, we took q, and then we took qd. Again, it comes from some log where you saved all qd, q desires. Okay, so once this comes out, what we have here is effectively plus minus plus minus. What comes out here is q minus qd, so I need to take this, multiply with kp. What comes out of this is q dot minus qd dot, so that's to be multiplied with kd, this term, and then this goes to another summation block. Let's put that block here. Negative, negative because of this. And then I need to also get in q double dot, so that also comes from some kind of a stored a table or something which like a computer which can supply the values for q double dot, and that is positive. And so all these terms get multiplied with the estimated mass matrix. So what I need to do is I need to have a m hat here, which then feeds in here. So this is some plus plus plus. So it's pretty complex. I don't think we'll have anything more complex in this, but this basically depicts the control partitioning law for trajectory tracking. Okay, if you want to do, if you want to add feedback, sorry, add integral control, which you might need to do if there is a steady state error, the controller will look like this: m hat q double dot minus kp q minus q qd minus kd q dot minus qd dot minus ki integral q dt. It should be q minus qd. The integral should be over q minus qd dt. Okay, that finishes things inside the bracket, plus c hat q dot plus g times q. So it's by far very complex, but it will get the job done. Okay, again, recommended for steady state error. Okay, so this is nothing too, well, it looks very complicated, but it's really a very small change over what we've done so far. We just added this term and this term, right? Which is q minus qd. That's all. I'm going to show you simulations which achieve trajectory tracking. And what I'm going to do is it's in a folder which I'm going to share. That folder has today's class. There are three things. Okay, go 1 to 3. Number 1, how do you use the files? I created a README. You just have to follow the README. Okay, the goal is to move the pendulum from 0. This is going to be that 0. This is 0. The horizontal position 0. Pi by 2, which is vertically up, in 1.5 seconds, and then back to 0 in 1.5 seconds. So it goes this. Okay. What you do first is, you know the initial position, you know the final position. You have basically 6 conditions: position for the horizontal, velocity for the horizontal, acceleration for the horizontal, which is 0. For the vertical position, you have position pi divided by 2, velocity, acceleration is 0. So there are 6 terms. You can assume a fifth order polynomial, fit the constants, which gives you the trajectory. Once you have the trajectory q as a function of time, this is your previous one of your homeworks, then you can find q dot by differentiating, q double dot by differentiating. Actually, it's not q dot, but it's q t, or your desired. And that is actually all that work is done in a file. I didn't do it myself on by writing equations on paper. So this file actually shows you how to do. Oh, by the way, my bad. I did not consider acceleration constraint. I did not consider acceleration of 0 at the horizontal or vertical. I just had 4 conditions: position, velocity, position, velocity. So that's why there are only 4 constants for the up path. So what I do is I fit a third order polynomial because there are 4 constants. Those a1s is 10, a11 for up, and a20, a21 for down position. So this way, going vertical to horizontal. Essentially, this code, you can check the code. Basically, writes what you do on paper is written on as equations, and it basically solves for the constants. In this case, the constants are the a's. Okay, and then you got to copy these. So copy, and then go to one link main. They have been copy pasted here, I presume. Right there, they have been copy pasted here. Okay. Just that how I wrote the code. You could actually write a function which will automate the process of copying, but it's not worth it, so I did not do that. Anyway, so once you have these constants, this is the theta a. So this is, by the way, a single link pendulum. So that's theta a, which is clearly a third order polynomial, and then theta a dot. You could differentiate, but I just wrote down the formula, which is derivative of the first one, and then acceleration, which is the second derivative of position, and that's for a is for up, b theta b, and so on are for up to down. That is fed into. There are a bunch of other things which are not used, but you could play with them, disturbance and so on. I'm skipping those, but they are basically fed into one link code RHS, which basically is the equations of a single link pendulum. So let's run this. Okay, it goes up and down. What I did was, my metric for seeing how well it fits the data is to use, well, I could do plots. Here is a plot for position. You cannot see the reference here. The reference is dashed line, and the actual is the line, because it's actually superimposed so well. It actually matches it perfectly that you don't see it. I should have used a different color. But one way to quantify the tracking is to look at the error, right? Each point there is an error, and if you take that error bars and then you just find the root mean square, that error is 10 raised to negative 15, negative 6, almost 0. So it's very good tracking. Now this was actually done with kp equal to 0. Okay, the feedback controller was not on. So it's interesting. The feedback controller was not on. It still tracked, and that's because we started the system perfectly at the initial position. There was no disturbance. We had perfect model in a perfect world, in perfectly tracked. The controller has a role to play only when you go off. Okay, so in order to get this system to go off, you can start it either in a different position, or and another way of doing that is to have an error in your estimate. So it's all these things I'm telling you is in this file. So set that the mass equals to params.m1, put kp1 equals 0, RF is 0, that's what I showed you. Next, set params to mass plus 0.5. So what I'm doing is I'm saying that, by the way, I'm not able to estimate the mass properly. It's off by 0.5 kilograms. Okay, my estimate is above the normal one by 0.5. Now let's run this and see what happens. So here I introduce 0.5. So now, because my model is incorrect, I'm expecting the tracking to be poor, and you can see the RMSE was actually pretty bad. So it goes up and off is an offshoot and comes back. It doesn't quite do what it's supposed to do, and that's because now we have a case where we have an incorrect model. Done, yeah. So the dashed line is what we wanted. The blue line, the red line is solid line is where what it is doing. Clearly, it's off. It's off, and so this is where the controller kicks in. You could get in the controller and get it to do better. And so let's take KP1. Let's make it 10. Okay, and this is supposed to be critically damped. So you see 2 square root. So you see that as you increase that number KP, you get better and better tracking. So I turned on the controller, and that's my error. It's decreased by a factor of 10. This is the tracking. It's sort of, there's still some overshoot, looks like. Yeah, see, it's not doing perfect tracking yet. Let's look at the plots. It's getting better, but it's not there. This is because my mass estimate was wrong. So it should be on the dash line, it's not on the dash line. Let's increase this to 100. So it's got down a factor of 10 again. And now I'm expecting it to be fairly good tracking. Still, it looks like an error. Let's see. So let's look at the plots. So that's better. You can see there's an error. That's why this is not equal to 0. If it was perfect, it would have been 0. This is the velocity as a function of time, position as a function of time. So you could technically go up on the gain here, and at some point it'll break. It'll break not because of the noise. There's no noise. It'll break because my integration has certain tolerance. So I think 10 is to, this is the most you can go. 1000. Okay, done. It's perfect, right? You can barely distinguish the reference, the dashed line with the solid line. It's perfect. So there's more in this code. I just showed you what happens if what happens if you are not able to estimate the mass, but you could play with other things, like you could add noise. So if you want to add noise, then this is adds the mean adds. It's like a sensor calibration error. If when the torque should be 0, it actually reads say 5. That's what it's going to introduce. If you put deviation, that's going to be noise. So this is noise in theta 1, theta 1 dev, sorry. And then you could add noise in the velocity. So if you want to add, let's say, noise in velocity, let's put let's say 0.5. Because you're adding noise, I would recommend introducing a controller. That's pretty good. The noise was not large enough. Let me ramp up the noise. Let's make it 2. Okay. Oh, it's still good. Yeah, you can see it's sort of jerky. I think that'll show up in the data. See, yeah, see, it's jerky. So you'll see that if there's a critical value for the gain when it works well. If you increase the gain too much, then you'll amplify noise. You'll get something like this. And if you keep it too low, then you'll not get good tracking. So there would be a compromise. There'll be a optimal gain, but that's something you can try. Okay, like this. Okay, so that's one example. What do I have more? two links. So I just went ahead and did two links now, which is slightly more complicated, but the ideas are all similar. Two link main, and I think for this again file I have a README, which I hope will help you to navigate through what's going on here. So if you open the README, okay, link 1 traj, link 2 traj are used to find position velocity, which is to run how to run simulate the case when you have perfect model and no feedback. Okay. Okay, so it's very similar essentially, just that it's tooling. I forget what the reference angles were, but let's just play this file and see what's going on. I don't remember what it's supposed to do. Okay, let's run this. I think all of them, oh, there's already an error, so I'm going to do this to 0. It already has a gain, so let me put that equal to 0, 0. Yeah, let's run this. So the error looks fairly close to 0, I think. Oh, it's supposed to simulate, I remember now. So it's supposed to simulate a kick, right? So you move your leg backwards, then you go forward. So I think it's like, so this motion is generated by figuring out what the angles should do at the two elbow and shoulder in order to achieve that. It's all in the trajectories are here, link 1 traj. So that basically solves for the first link. Okay, so I want it to be in 3 seconds, so the first link should move for a time of 3 seconds. Theta 1 0, which is the initial position, is this, I think it's pi minus 0.5. So it's slightly, so it's basically, see, pi by 2 is 90 degrees and then 0.5, so it's fairly back, okay, this way. And then it goes, I got to plot this. I'm not sure of what I mean by pi. I think if you look at the plots, you should figure it out. Link 2. There are two profiles for the link 2. So I think one of them is the backward motion, one of them is the forward motion. 1.5 seconds first motion, you can see here. And then the second motion is for another 1.5 seconds. After running this, you get the constants, which are supposed to be copy pasted into this code. Yeah, those constants come from that code. Anyway, so you can, the instructions are there. You have to basically put an error in the mass matrix, like so the move from, I'll call it this x initial to x final, where this, it's actually a Greek word, I don't know what it's called, where this x is basically xi, yi, zi, and xf equals xf, yf, zf. Okay, so the initial final points are given in time tf. Okay, so initial time is 0, final time is tf. We want to go from point A to point B. How do we do that? So In other words, first thing you do is find xd using a polynomial or whatever you want to use for figuring out the trajectory xd of t, xd of t using the polynomial of appropriate order. The next step is find qd dot qd double dot of t using inverse kinematics. Okay, so once you have qd, then use control partitioning with trajectory tracking, right? Because now you know of the trajectory qd dot and so on. So this is how we do. Step 3 is basically saying tau equals, so right here. So step 1, this comes from the trajectory generation. I'm not going to specify that. Number 2 is find qd dot and so on. The way you do it is xd equals f of q of d. This is your forward kinematics. Okay, qd in that case is going to be f inverse xd. This is the inverse kinematics. We've talked about inverse kinematics in the class previously. You had to, there's a homework too which involved finding the joint angles so that you achieve a certain position. But we need more than that. We need qd dot and qd double dot. So this is how you do it. So first we'll differentiate x. So when you differentiate this, you get x dot is j times qd dot, right? This is basically an approximation to x dot, basically first order approximation, right? Yeah, first order approximation. That's the Jacobian which we talked about in this course. And once you do that, then what you do is qd dot is j inverse xd dot. So now we know qd, we know qd dot, we don't know qd double dot. So what we do is essentially take this expression, differentiate it again, so xd double dot, to get and differentiate the right side, then we'll be able to find qd double dot. So let's differentiate xd double dot equals j dot qd dot plus j. So this is using the chain rule. Okay, and so we need to find qd double dot, which is going to be j inverse times xd double dot plus j dot q dot. Okay, so the things on the right side are known. This is known, we just found it. J dot you can find, x double dot j is known, so qd dot is known, and that's what goes into your third part, which is the tau is the mass matrix. You estimate q minus qd double dot minus kp q minus qd minus kd q minus q dot, that closes the bracket, plus c hat q dot plus g hat q. So that's your control law. You already have found q double dot, this should qd and q dot. So we have all that, and that goes into your simulation. So the last example, the Matlab file, is about simulating the lemniscate, which you've seen probably in the class. So example, which is a Matlab example. Okay, which is going to be drawing the lemniscate. Figure 8. Lemniscate is also known as the figure 8 or infinity, some people. Figure 8. So it's also called the lemniscate. So see Matlab. So let's go through Matlab and see how it is done. That's the last thing. Okay, so this is going to be the third file. If you go to my lecture 20 Matlab scripts, the third one, open that, open the README. So we want a two-link manipulator. You cannot do it with one link. You need at least two links, because X, Y, you need to have the end effector move in X, Y space, and you need at least two joints to do that, because there are two things which are asked for, X and Y. Two-link underscore track generates the trajectory. Okay. First, end effector position using smooth times function curve. Second, using time. Okay, let's just see what's available here. Let me open the two-link track. Okay, so it looks like in this file I'm estimating J and J dot. And I just use Matlab to do it. I don't really do any computational plan. Of course, I need to specify J though. That computation comes from, I think I already have the J's. I found it in an earlier, it's a two-link manipulator, so I found that in the previous class. Let me just run this. Maybe this will not run. Okay, so this actually is called by another file, so it won't run. The main file always is the one which you want to call, two-link main. Let's call this one. Okay, so initially, if you read this file, I think I've said set the KP1, KP2 to be 0. There's no feedback control. Run the tooling file, and let's see what happens. So the error is huge. 4 is quite big. Okay, that's not figure 8, clearly. Okay, the reason is, so here's the interesting thing. Previously, I showed you that the model was perfect. When we do the feedback control, we got perfect tracking. Here, the model looks perfect. We have no feedback control. It should have tracked 8. The reason it did not track the figure 8 is because there was an approximation. When we talked about finding the inverse, finding xd dot from q dot, we actually had j. That j is an approximation, the first order approximation to the forward kinematics. So our model was incorrect, but it was incorrect in the inverse kinematics, not in the m or c or q. So because of that, we were not able to draw the figure 8 perfectly with zero feedback gain. What we need to do here is increase the feedback gain, and I'm going to just go and make it 100. Let's see if it does a better job. The errors will tell me whenever it finishes. So that looks better, 0.0 and 0.16. I think it probably draws. Okay, so that was better. You can look at this is the velocity. Let me get to, yeah, this is better. So this is stating what the joint angles need to do in order to draw the figure 8. Clearly, that's not intuitive, right? Can you predict by looking at those plots what the end effector would do? These are telling you what Q1 and Q2 would do. So it's very it's not easy to figure that out unless you do this inverse kinematics, which I just taught. You can see that the dashed line is not exactly on the solid red line. That's because they're tracking error. And so if you ramp up the gain, you'll actually see that this will go to almost 0. But if it looks like that 8 is kind of okay, doesn't look there's an error, so it's okay. So you can actually also try to add some noise, add a error in the mass matrix and see what happens. You'll see that you have to increase the gain much more in order to track that curve perfectly. Okay, so that's, and the equation, all the equations for lemniscate are somewhere buried in the code. I think they are, well, they are here. Let's see. I think the equations should figure in figure 8. So there's a file called figure 8. Okay, this is basically the equation of a lemniscate, which was in that 50 curves. Okay, so that's all I had to say. I was expecting a student to come and show you the demo for a manipulator drawing the figure 8. Let's give him 5 minutes.